Welcome back for another flight computer video. Today we are talking about the DR2 Dreieckrechner, or triangle computer made by Dennert Pape. And we don't have to guess about the date on this one. It's printed right on there from May 1940. So this flight computer comes from the middle of World War II, and it was the standard German dead reckoning computer that was issued at the time. In this video, we'll just quickly talk about the construction of the device and also do a wind problem, and I'll save some of the other details about the flight computer for another video. So on this side of the device, we have two movable scales. This white scale on the outside moves. This black scale here does not. It's attached to the base. And the inner white scale moves as well. So the outer scale is a trigonometry scale. It's a sine scale. The inner scale is a logarithmic scale for speeds or distances. It goes from a unit of 4, it's 2 decades, so it goes from a unit of 4 all the way around to 40, and from 40 all the way around to 400. And then the inner scale here is used for time, and it's marked from time units of half a minute all the way up to 5 hours. There's also these interesting little pins for moving the cursor into position and moving them together. We'll take a look at those in a different video. There's also this red band right here. That red band represents airspeeds that were common at the time. So 250 kilometers per hour up to about 385 kilometers per hour, roughly 130 knots to 195 knots or so. And we'll use this as we do our wind solution here in just a bit. On the other side of the device, same thing, the black scale does not move, it's affixed to the base, and we have a white scale that does move, along with a two-sided cursor for helping us with our wind calculations. And I think now is probably a good time to just jump right on into that. So let's go ahead and solve a problem on the DR2. And this is the problem that I wanted to solve today. Now, I've drawn out the triangle to help make the math a little less abstract. But all to say, you don't actually have to draw a triangle in order to know how to operate this device. So this is our standard wind triangle problem. We know a true course. We want to fly a true course of 310 or to the northwest. We know our true airspeed, and we have a forecast wind, and the wind is coming from 090 at 65 kilometers per hour. So that's what I've drawn here as a vector. And to sync those up, what I've done is I've done this to scale. I've picked off a distance that represents 300 kilometers per hour. And from the outside of my wind vector, I can swing an arc in order to find where it meets my true course. And that's how my triangle is drawn. Again, you don't need to draw this triangle. It's just we'll reference this triangle as we're trying to figure out how it works trigonometrically. So let's just start putting things into the computer and go from there. So first, our true course is 310. So we take our airplane and we point it to where we want to go. So I point it to 310 here on this outer scale. Next, I take my double-sided cursor and I set it to my wind, which is coming from 090. And from there, on this inner white scale, I can read my relative wind angle, or the distance, or the angle between where I'm going and where the wind is coming from. And you can tell that that's more than 90 degrees, it's 140 degrees. We're gonna need that value in order to solve the wind triangle trigonometrically. You'll see how in just a second. I can also write this down here. So if my wind angle, relative wind angle, is 140 degrees, you can tell that that's the outer angle. The inner angle here will be 40 degrees. Okay, so now we flip the device to the other side, and what we want to do is use the law of sines in order to calculate our missing values of our wind correction angle and our ground speed. So we do know, again, that this angle right here is 40 degrees, or the exterior angle is 140 degrees, and we know the length of the side opposite that angle is 300 kilometers per hour, which is our true airspeed. So we set that up on the computer by finding 300, which is right here in the middle of the red band, and we set our desired relative wind angle across from that. So I've set 140 here across from 300 kilometers per hour. And I actually don't have to manipulate the device anymore. Everything, all my answers are now there waiting to be found. So the first thing we want to do is find our wind correction angle, which is this angle that's right here. We know the length of the side that's across from that angle is 65 kilometers per hour. And because we've already set up this ratio between the relative wind angle and our true airspeed, all we have to do is go look across from the value 65 on our distance scale and read the angle that's there. So here is 60, bring it on up. Here's 60, here's 65, and as we go across, we see that we've got an 8-degree wind correction angle. So this value right here is 8 degrees. I'll write that over here as well, 8 degrees, and we'll have to be correcting right, of course. So our on-course heading here will be 310 plus 8 degrees, or 318 degrees will be our true heading here. And now that we've found our wind correction angle, we can find our ground speed by subtracting our wind correction angle from our relative wind angle and looking at the ground speed across from that angle. Now, why does that work? Well, we know that all three of these angles here, these inner angles of this triangle, have to add up to 180 degrees. So this one was 40, and this one was 8, and we subtract 180 from there. What we're doing is we're looking across from the number 132, or angle of 132. And so, here we go. I'm gonna do this with the cursor to make it a little easier to see here. We've got 140 set there. All right, so we go to 132, which is right here, and that gives us our true airspeed, which we can see is between 340 and 350 kilometers per hour. So a ground speed of roughly 347 kilometers per hour. So that's how we solve the wind triangle with trigonometry. And no dots are necessary, no wind dots, no drawings. It's just purely with math. And so it's quite different than the E6B as a way of solving a wind triangle, where we did essentially just draw a triangle. Here we're doing it purely with math. And I think, you know, it's not that one device would be better than the other, but if you are more mathematically minded, you may really prefer this way of solving the wind triangle. And if you don't like math, then, well, you might prefer to just draw a wind dot and manipulate the device to find your answers. But it's fun to look at these two devices at the same time and realize that these were essentially, this is what was fighting each other in World War II on the Allied side and the Axis side. So that's all for this video. If you're interested in knowing more about the DR2, there'll be a follow-up video, and you can check that out when it's available. And thanks for watching.